So when I started micro, I told you that the story of microeconomics that we are going to look at is basically the story of Adam Smith's invisible hand statement. So what was the statement? The statement says that uh, if people just work for their private benefit, then it seems as if the economy reaches an efficiency level, as if some invisible hand is guiding the economy, it's guiding the agents. So what Adam Smith basic basic inference from this invisible hand statement is that utility maximization, or rather private benefit of individuals, leads to efficiency of society. This is basically what the invisible statement means, implies. Now, Adam Smith did not explain in The Wealth of Nations, he never explained what is the meaning of private benefit. Like, is it profit? Is it more money? What is private benefit? He never explained what is efficiency, and forget the proof altogether. Okay, so giving proof is completely out of the picture. He didn't even care to bother what does it mean by private benefit? What does it mean by efficiency? So private benefit, as we have discussed, is something which came to be known as utility. Utility, and then agents became utility maximizers for consumers, and for producers, private benefit means profits. So private benefit means either utility for consumers or profits for firms, and efficiency was defined as Pareto efficiency. So this was the job of utilitarians, John Stuart Mill and others. This was the job of Pareto, defining efficiency. And this proof came in by Arrow. So Arrow gave the proof that utility maximizing and consumers and profit maximizing firms, if you put them together in a society, then the society will operate at Pareto efficiency level. So it's not that one person could give this proof of this statement. The statement was so powerful, it took us almost a century from when Wealth of Nations was, 2 centuries. He wrote it in 1776, and Arrow proved it in about mid 1900s. So, so it took us 2 centuries of entire journey, which we have taken here in the past 20 odd lectures, to see what is utility, what are profits, how are they maximized, and now we'll see the final picture and what is Pareto efficiency. But the general equilibrium, it says that when you have all sorts of consumers which have different utility functions, and they are all utility maximizing, different firms which are all profit maximizing firms, then the market becomes too complicated to analyze. So we are going to look at a simpler format wherein we have only consumers, only endowed consumers, in an exchange market. So generally, you understand the market is very dynamic. Consumers are endowed not with goods, they are endowed with certain characteristics, like somebody can be smart and he can perform, he can write algorithms. Somebody is a good driver, somebody is good at playing tennis, somebody is good at playing football, somebody is good at singing. So different people are endowed with different things, and then the market pays for people to perform according to whatever they are endowed with, and they get paid for it. And when they get paid, they use this income to purchase goods, and then comes the picture of profit maximization and all those things. So you understand, it's very complicated. but you will look at that complicated thing as well at your master's level. Right now, we are going to look at an exchange economy. So what happens in an exchange economy is we have a separate island where we only have consumers, and each of these consumers is endowed with some amount of goods, like they are born with some goods. So suppose this guy is born with, let's say, butter. This guy is born with bread. This guy is born with eggs. And how they come together and they decide, let us build omelets. Okay, so this is usually what happens. So if you understand, if you have ever been to such parties where uh, you and your uncle's family and maybe your aunt's family, all three of them decide, okay, let's go to India Gate. We'll take, one person brings the sabzi, one person brings the puris, the other person brings something else to the table, and then together you all exchange whatever you brought. This is something which also happens in tiffins. When you have tiffin in your classroom, somebody bringing something, somebody else, and you exchange. Okay, so there's no scope of, earning money and then buying it. Everybody comes endowed with something and then they exchange with each other. What we are going to find out that how will this exchange work? How much of what good will be given by what person to whom, and what will be the equilibrium of this, of such an economy. So that's going to be an exchange. Okay. So in order to study the exchange economy, so consider that you have two agents, just two agents right now. So we are going to start with two agents, but whatever math we do, it will be applicable for higher order, that is more agents as well. So we generally study 2x2 exchange economy, where the first two stands for number of agents and second two stands for number of goods. Now you can have multiple other combinations. You can have three agents having two goods. You can have two agents having three goods. Okay, so 3x2 and 2x3 are still something which is within the scope of this exam. They have been asked it previously. But more complicated things like 3x3, 4x4, 4x3, such things are not really there. So barring two questions throughout history, I think all the questions have been based on 2x2 exchange. So you have two people who are exchanging two goods with each other. So suppose the agents are OA and OB. So this is, let's say, origin of agent A. This is, let's say, origin of agent B. Agent B's endowment is some point XA comma YA, and agent A's endowment is some point, oh no, this should be XB. So I'll come back to that. XAYA here and XBYB. So now what happens is, suppose this is the economy and they exchange with each other. So agent A's endowment vector, if I call this as EA vector is basically XA comma Y. So this is what you call as, let's say, EA vector. And agent B's endowment is, let's say, EB vector, which is XB comma Y. Now, if these two people exchange, let's say A takes everything that B has away from. Let's say B donates everything, or A is powerful, he takes away everything. He has a gun, he can shoot B. So he takes away everything B has. So what is the maximum point where A can reach if he can basically take away everything from B? On this
XA plus XB comma Y plus Y.
XA plus XB comma YA plus YB. Great. So that is basically EA vector plus EB vector. So if this is my EB vector, this guy will reach EA vector plus EB. So this rectangle, if I write down this rectangle is basically the scope of all possible points where A can reach. So if all he could do is either give or take, then the max he can do is some point in this rectangle. If he gives away, if he takes away from A, then he is going to strictly lie in this rectangle. In this rectangle, any point in this rectangle is you are gaining something from A. If you are strictly just donating something to B, then you will be in this rectangle. Okay, so you lie in this rectangle if you take from B. You lie in this rectangle if you donate to B, and the remaining two rectangles are the rectangles of trade. These two rectangles represent trade with. So basically, if he from this point, suppose he moves to this point. So what's happened is he has given up some amount of good Y. He has given up some amount of good Y in exchange for some amount of good X. So delta X is positive and delta Y is negative. So agent A has given up some amount of good Y in exchange for some amount of good X. So different regions. So here the opposite will happen. Here you will see delta YA positive and delta XA negative. So different region correspond to different sort of situations. What can happen, but whatever happens, donating, taking away, trading X for Y, trading Y for X, whatever happens with A, he will be restricted inside this box, which has dimensions EA vector plus PA vector. Similarly, if you analyze things from B's perspective, his world is limited to EB vector plus EA vector. So what happened is Edgeworth saw this thing, and what he summarized is that whatever happens, doesn't matter, donation happens, seizing happens, or trade happens, whatever happens, it happens within the confines of this Edgeworth box. And both agents are restricted in this box, which later on came to be known as the Edgeworth box. So the edge, what he did is, what Edgeworth did is, he took this rectangle, he rotated it by 180 degrees, and he superimposed it with this rectangle. Because both rectangles have the same dimension, they perfectly fit over one another. What happened is, because he rotated it by 180 degree, this OB, which was the origin of agent B, it now came to this one. So now you do not need two different figures to analyze the endowments of the agent. One rectangle, which came to be known as the Edgeworth box, was sufficient to basically represent both the agents' endowments and any possible movement from those endowments as well. So let's draw this Edgeworth box and see what's happening. So in Edgeworth box, the standard thing is the bottom left corner is the first agent origin. The top right corner is the second agent's origin. That's convention. Now, the endowment point of agent A is EA vector from here. And endowment point for agent B is EB vector from here. Now, since this point is EA vector plus EB vector, right? OB itself is EA vector plus EB vector. What that implies is that the endowment point of both these agents will be coincidental. So this same point will represent the endowment of agent A as well as endowment of agent B. So you do not need two different points on this box to show the two endowments, because EA plus EB is OB. OB is the point EA plus B, because that is the dimension of the Edgeworth box. This Edgeworth box's dimension is EA vector plus B vector. This is basically dimension of the Edgeworth box. So this is basically XA plus XB comma YA plus YB. So the base is XA plus XB. The height is YA plus Y. Okay. And this point is XA, XB, XA plus XB comma YA plus Y. This origin of agent. Now let us analyze any trade starting from this point of endowment. So let me remove all these things. Let me use a clearer picture. So suppose this point is let's say suppose XA comma YA is 2 comma 3 and XB comma YB is 5 comma 6 comma 1. Okay. So OB is going to be the addition of these two things. So that's 8 comma 4. So that's OB. And this point is simply 2 comma 6. Because all points are measured with respect to origin of agent A. Origin of agent A is 0, 0. Origin of agent B is now 8, 4, because all points are measured with reference to this origin. Now, suppose you have a trade where A gives 2 units of X, 1 unit of X to B, and gets 2 units of Y in return. Right? So A gets 2 units of X and B gives 2 units of Y. So right now, both these points are coincidental. So I'm drawing the 2 points, but they are at the same location. By the way, the blue and red points are at the same location. So what happens with A is he gives away 1 X. So his X reduces by 1 minus 1. And his Y increases by 2 plus 2. Okay. So ultimately, A reaches this point. So let me call this as XA vector. EA vector was the initial endowment. XA vector is the allocation or the point he reaches after trading. So minus 1 on X and plus 2 on Y. Now let us look at what happens to agent B. So agent B loses 2 units of Y because he's giving away 2 units of Y. So his Y reduces by 2. But this is the origin of agent. So Y reducing by 2 means Y goes in this direction towards the origin. So this is the X-axis of agent B. This is the Y-axis of agent B. So you move towards the X-axis of agent B by 2 units. So since you're going up, I'm calling it plus 2, but actually he is losing 2 units of X. But since all movements are measured with respect to origin of agent A, I'm going to go up. And he gains 1 unit of X. So gaining means you move away from the Y-axis. So he's going to move here by plus 1 units. So he's also going to reach here. Okay. So the point is, any trade will again move these people to the same point. Whatever trade happens. So they start with the same endowment point, and then whatever trade happens, they move simultaneously inside the Edgeworth box. So depending on what trade happens or what donation happens, whatever happens, they move either here or they could go here, or like in this case, they could go here or here or here. Wherever they go, as long as the trade is non-wasteful, as long as the trade is non-wasteful, they will move to the same point on the edge. Now, what do you mean by trade being non-wasteful? It means nothing should be discarded. It's like if I give him 1 unit of X, he should not be like, I don't want it, I'm throwing this. Trade should be non-wasteful. Because if he throws away that amount of X, then what happens is that he only reaches this point. I give him X, he threw it away. So now what happens is B reaches this point, which is different from X. So the trade has to be non-wasteful. So as long as you assume, and non-wasteful trade is an assumption of general equilibrium. So as long as trade is non-wasteful, these two people will move simultaneously. So you do not need to verify two different points. Only one point is sufficient. So let's do a quick example.
Sir, I didn't get that 2,6. Like, should be 2,3 or what? I don't know.
Oh yeah, sorry, 2,3. Sorry, this is 8,4. This is 2,3. Yeah, sorry, my bad.
Okay.
Okay, let's do a quick example. Suppose endowment of agent A is 3,5 and endowment of B is 5,3. So what will be the dimension of Edgeworth box?
8,8.
8,8. So you just add them up. 3 plus 5 is 8, 5 plus 3 is 8. Okay. If X gives, so A gives 1X for 2Y, what will be XA vector?
Two comma 7.
Yeah, 2,7. Exactly. So he gives 1X. So his starting point is 3,5. So from here he gives 1X. So this guy becomes 2 and he gains 2Y. So this guy becomes 7 to 2,7. So this guy's endowment automatically becomes 6,1. The remaining must be with him. Now the idea is nobody's endowment can be negative. We are not discussing antimatter. Okay, we are not physicists. For us, things should either be 0 or positive. They cannot be negative. So anything going in negative is not allowed. So A giving 4 units of X will not make any sense to me. Or getting 4 units of Y again makes more sense for me because EB is maximum 3. The maximum YB can give him is 3. So there's no way this guy can get 4 units of Y. So any such thing is not possible within the confines of the Edgeworth box. So you can only rotate yourself inside the Edgeworth box. And it's like you're tied together. You cannot move away. So if I move here, you also move here. Both agents will move simultaneously. So that's Edgeworth box for you. Now I've used X and Y. Sometimes some textbooks use X1 and Y1 as, sorry, X1 and X2 as the goods. The goods are X1 and X2. And the agents are also 1 and 2. So endowment of agent 1 becomes E11, E21. And endowment of agent 2 becomes E12, E2. Gets little complicated. Some textbooks use these notations. The good thing about these notations is if you're just using indices 1, 2, 3, and so on, you can go for any N cross N exchange economy and apply your results there. When you're using X and Y, you're limited by जहाँ से आता Z कर लोगे फिर उसके आगे क्या करोगे. Okay, so beyond 3,3, X, Y as goods, X, Y, Z as goods make sense till 3, till you're working with 3 goods. If you're more than 3 goods, you can have problems. But since I told you, we are mostly going to look at 2 cross 2 cases. So that's why for us, it's okay. Some higher level books which want to deal with n cross n results as well, they get into using x1, x2 and agents as 1 and 2. The easier thing for us would be using x and y as the goods and a as b, a and b as the agents. That's going to be the easiest. Okay. Now let us analyze any endowment point and try to think what will happen. So suppose this is some Edgeworth box in which this is my endowment point. So if I separately draw the 2 agents consumption sets, so agent A's consumption set will be like this, XA, YA, and agent B's endowment will look like this. In XB and YB, it will look like this. So it will be 180-degree flip of what you are seeing. Now, the goal of any agent is utility maximization. So first, let us draw the indifference curve of this agent. So indifference curve of this agent passing through his endowment looks like this. So if I draw it on the Edgeworth box, it will look like this. Indifference curves do exist beyond the Edgeworth box. Okay, because if you look at what agent A's world is really, agent A's world is really this thing. This entire thing is agent A's world. Right. So his ICs can extend beyond the confines of Edgeworth box. But the problem is that these points are not feasible. So it is okay if you draw these ICs beyond the confines of Edgeworth box, there's nothing wrong. Or you can strictly stay within the confines, doesn't matter. Agent B's IC is also convex. So when I flip this by 180-degree, it will start looking like this. His IC, by the way, can look like this because agent B's world is here. This is his consumption set. So his ICs can go beyond the confines of Edgeworth box in these 2 directions. But it's okay if you draw it, if it's okay if you don't draw it, up to you. But the point is, starting from this endowment point, these are the ICs of these 2 agents. Now we say that voluntary trade can happen. What is voluntary trade? You come with bread, the other guy comes with eggs. You are like, bhai, mujhe ande de do, main tumhe bread dunga. That's voluntary trade. Okay. You come with gun, the other guy comes with gold. You show him the gun, he gives you the gold. That's not voluntary. Okay. That's robbery. So we are not allowing for robbery or coerced trade. Coerced trade is the government taking taxes and giving you highways in return. Okay, it's not voluntary. Government says tax though, we'll give you highway. And then they open a piggy bank and then you put money in it. That would be voluntary. Government says tax though, warna hum log usko jail mein dal. So that's not voluntary. So those are examples of non-voluntary trade. Voluntary trade means there's no coercion. People do this because it improves their utility. Okay, so all agents in a voluntary trade engage because either it's increasing their utility or they're indifferent. Nobody will engage in a voluntary trade if it makes them worse off. Okay, so nobody engages in a voluntary trade if they are worse off. So why does Vijay Mallya not pay taxes? He says, I don't need highways, I have a helicopter. Why should I pay taxes for highways and railways? I have my own flights. I have my own helicopter. I don't want to pay taxes. So that's why we have coercion. But let's come back to A. This is indifference curve of A, and agent A's utility increases in this direction. So he goes anywhere above this blue curve, his utility goes up. So in the Edgeworth box, that region is represented by this. He goes anywhere in this region. Should we use blue actually? So agent A, he moves anywhere above this IC, his utility will go up. Okay, anywhere above. Agent B, on the other hand, also wants to go above his IC, which when you rotate by 180 degrees becomes this region. Okay. So you see this intersection, this green region is the region in which both of them get better. So if they reach any point in this green region like this, they can both be better. So that's the idea of efficiency that we are looking at. So we say, let us define efficiency. Uh, So let us define Pareto efficiency. In order to define Pareto efficiency, I first need to define what is Pareto improvement. So what is Pareto improvement? So Pareto improvement is that if the idea is that if at least one person can be made better off without making anyone worse off, then it is called a Pareto improvement. Okay. So we consider two different situations, X and Y, and we say that as compared to Y, as compared to X, so let me call this position as X and this position as Y. Rather, let's go with some other L and M. Let me call this position as L. And this position as M. So in situation M, everybody is better off as compared to in situation N. So that's a Pareto improvement. Okay. So at least one person, it's okay if everybody gets better off, but if at least one person can be better off without making the other person, then we say that in this situation, M is Pareto improvement over N. Okay. So in this same figure, let me erase the colors. They are getting a little difficult to focus on. So tell me if this point N on the edge of this lens, N, is N a Pareto improvement over L or not? Is this statement true or false?
Sir, it is true.
Why is it true?
Because for L, it is on the indifference curve.
For A, yeah, for A, it is on the indifference curve. Yeah.
And for B also, sir, L is on the indifference curve for A and B both, no?
Yeah, L is on the indifference curve for A and B. Yeah. L is the starting point. I'm saying if you move from L to N,
Sir,
will
B
this
gets
be a
better off and A remains the same.
exactly? So one person is better off. So that's your person B. And nobody's worse off. Nobody's worse off at N. Okay, so that's why N is a Pareto improvement over L. Okay. Okay, tell me about this point P. Vinay, why don't you tell me, is P a Pareto improvement or not? Very good. Is P a Pareto improvement over L or not?
So they both seem the same.
So the answer is yes or no. Is P
No, sir.
Pareto improvement? Okay, very good. So this statement is false because you need at least one person better off. You see, P is on the same indifference curve for A and B. So between P and L, what's happening is that between P and L, what I'm seeing is that P is indifferent to L for agent A and P is indifferent for L for agent B. So both the agents are indifferent between P and L. So none of them is getting better off. So at least one person should be made better. Okay. If nobody is getting better off, then that's not a Pareto. Okay. So to give you a quick example, a numerical example to make sense of this thing. Because the idea feels कि सबका फायदा कैसे हो सकता है? How is everybody getting better off? So let's do a quick numerical example. So let's say utility A is equals to XA by A and utility B is equals to under root XB by B. Suppose the starting point is 2,4 and the total endowment is 6,6. Okay. So this is my point, starting point L, let's say, which is 2,4. This is origin of A, this is origin of B. So first of all, what is utility of A at point L going to be?
Root 8.
Root 8, very good. And what is utility of B at point L?
The root 8 only.
Root 8, yeah. So that's going to be under root of 6,6 minus 2,4. So that is under root of, sorry, a utility at 6,6 minus 2,4. So that is utility at 4,2. So this guy's endowment is going to be 4,2. Okay, so you subtract 6, 6 message, subtract 2,4, you get 4,2. So that is again under root 4 into 2. So that is. Now from here, if you move to another point, let's say 3,3. 3,3 is feasible for both of them. Right? Right now, total endowment is 6,6. Suppose they both come to 3,3. So what is, let me call this point as point M. So what is utility of A at point M going to
be?
3, which is greater than root 8. And same with utility of agent B, because he's also going to be at 3,3. So his endowment is 6,6 minus 3,3. So his vector is going to be 3, so utility of B at M is also going to be under root 3 into 3, which is greater than root 3. So you see, A and B are both better off. So this was your utility of A at L, and this is utility of B at L. So both of them reach a higher level of utility by trade. Okay, so this is an example of a Pareto. Moving from L to M, okay, so the movement from L to M is a Pareto. So now we define Pareto efficiency as, okay, a point E is said to be Pareto efficient if there is no other allocation that is a Pareto improvement over. So we say a point E is Pareto efficient if there is no allocation that is a Pareto improvement over. So how do I find these Pareto efficient allocations? So the idea is very simple. Suppose you have some starting point called E. This is on N, some starting and nominal. Utility of IC of agent A looks like this, IC of agent B looks like this. So they are intersecting. So in the intermediate zone, you will see Pareto improvement. So you move to one such location, which is, let's say, a Pareto improvement. Okay. So starting from this point L, you move to another point, let's say M. And you see that still at M, these indifference curves are still intersecting. So again, there is some region in between where you can find Pareto. So what you'll do is again, you'll move inside. So again, you move inside and you'll keep doing it till you reach a point where the ICs actually become tangent to each other. So this is a point N where the ICs are, let's say, or let's say a point E where the indifference curves are tangent. Now agent A, remember agent A's origin is here. So agent A wants to go above his IC. Agent B wants to go below his IC. So there is no common region where both of them agree on. So now there is no Pareto improvement, which implies that E is Pareto efficient. Pareto efficient. You call it Pareto efficient, you call it Pareto optimum, or you call it Pareto equilibrium. There are different words for it. Most common Pareto efficient, but Pareto optimum is also common. So the idea is that when both agents have convex preferences or well-behaved preferences, then Pareto efficiency will happen at the points of tangency of these two agents. Okay, so that's my first rule of thumb, that when both agents have well-behaved convex preferences, the tangency points of the ICs are this set of all Pareto efficient points. So the set of all Pareto efficient points is the set of tangency points of IC. It's the same thing. Okay, so it's not going to be like subset or superset. All tangency points are Pareto efficient. All Pareto efficient points are tangency points. Nothing else. Okay. So that's going to be the thing, that we have to find a set of tangency points when they have well behaved and convex preferences. So remember, from the first class itself, we have been doing a lot of analysis about convex preferences. The reason is that convex preferences is an assumption that Arrow made when giving the proof for general. If they're not convex, then we don't know. It's very difficult to find equilibrium. When they are convex, it's pretty. So convex, well-behaved convex preferences, so that's going to be the key. So what happens? How do I find the set of Pareto efficient points? So let's do another example. Okay. So let UA equals to under root XAYA. Let's remove root because, I mean, you can always use monotonic transformation. So let's just use XAYA. UB equals to XBYB. Endowment of A is, let's say, 2, 4. Endowment of B is, let's say, 4, 2. Find the set of all Pareto efficient points. I have to find the set of all Pareto efficient points. So it's going to be a square. What is the dimension of this Edgeworth box? What is the dimension?
So 6,6.
6,6. Great. So 6,6 is the dimension of this Edgeworth box. Now you're starting from 2, 4, a point like here. So a tangency will happen. Suppose the tangency happens at a point xa, y. Or generally, let me call it just x, y. So let's say this is the origin of agent. This is the IC of agent A, and this is the IC of agent B. And this is the tangency point x, y, or x, y. So what happens is, so this curve is, let's say, called ICA, and this curve is, let's say, called IC. So what I need is basically that the slope of ICA at XA, YA should be equal to slope of ICB at the same point XA, Y. I need this relationship. Now, what is slope of an indifference curve?
Sir, MRS.
Very good, MRS. So this is just negative of MRS. So negatives will cancel. So what I'll need is basically MRS of agent A at XA, YA should be equal to MRS of agent B at XB, Y. Sorry, at XA, Y at the same point. Okay. इसको हमने एक डब्बे में रख दिया. Now focus on these things. If this is the utility of agent A, what is MRS of agent A? What
So
is the
minus
formula?
of Y upon XA.
YA by XA, not minus. Slope is minus. MRS is just YA by XA. And similarly, MRS of agent B will be YB upon XA. Now I have the MRS of B at YB XB. I want MRS at XA YB. Now the relationship which is going to be the key is that XA plus XB is equals to 6 because total endowment of good X is 6, which implies that XB is equals to 6 minus XA. And YA plus YB is also equal to 6, which implies YB is equals to 6 minus YB. So when I make these substitutions here, what I get is that MRS of agent B in terms of XA and YA is 6 minus YA upon 6 minus. So finally, MRSA is YA by XA and MRSB is this. And then finally I equate these two guys. So what I'll get is YA by XA should be equal to 6 minus YA by 6 minus XA. What equation do you get when you resolve this? Solve this and give me the equation.
Sir, X equal to Y.
XA equals to Y. What does that represent? What does this equation represent in this box? What is this thing an equation of?
Sir, it is the line which passes through OA and OB and it is in the center of the box.
Very good. So it will be a line like this. Ideally, this point should have been here. So basically, this will be the set of all Pareto efficient points. All such points XA equals to YA are going to be Pareto efficient. So along different points, different indifference curves are going to be tangent to each other. Okay, along different points on this curve, different ICs are going to be tangent to each other. My question is this point Pareto efficient? OA.
Yes, sir. It lies.
Yes, it is Pareto efficient because the idea is to check Pareto efficiency. I have to find, is it possible to get a Pareto improvement or not? The definition of Pareto efficiency is when there is no Pareto improvement possible, it is Pareto efficient. So obviously tangency thing is difficult to analyze here because the IC through OA actually looks like this. This is the IC through OA. And the IC through this point for agent B will be like this. So obviously tangency cannot be figured out because this guy is not even differentiable. This indifference curve is not even differentiable at this point. So how do I check if it is Pareto efficient or not? So the idea is that you have to look at the original definition of Pareto improvement. So at point OA, utility of A is absolute. If you want to increase utility of A, you need to give him some amount of X and Y. But as soon as you give him some amount of X and Y, agent B's utility reduces. So there is no way at this origin, there is no way to improve A's utility without harming B. So that's why this point is also Pareto efficient. This point is also Pareto efficient, and all the connecting points are also Pareto efficient. Okay. So let's do a quick question. I've already given you this example. So let me add one more page here. And then, yeah. Okay. So the example that I want you to do is that again UA is XAYA, UB is XB, YB. Endowment of this guy is 2, 5. Endowment of this guy is 3, 5. What is the set of Pareto efficient points? By the way, set of Pareto efficient points is known as the contract curve. So what is the contract curve? So I'm opening up this solution for your reference if you want to use it. The solution for the previous questions here. Give me the contract curve.
So y is equal to 2xa.
Y equals to, yeah, that's correct. Because if you proceed in a similar manner from what we did earlier, then what we get is MRS of A equal to YA by XA, and MRS of B will be YB by XB. Since total endowment is now 10, this becomes 10 minus YA upon total endowment of X is 5, so 5 minus X. So this should be equal to YA by XA. When you cross multiply, so what you get is 10XA minus XAYA must be equal to 5YA minus XAYA. XAYA cancels out. So what you get is YA is equals to twice X. Okay, so this is going to be the contract. Finding the contract curve is pretty straightforward when you have convex differences. Is this done? No doubts, I hope. This is important, being able to
Yes.
find the contract. Cool. So now, next thing is, okay, contract curve ho gaya. Finally, I want to find, okay, so why do you use the word contract curve? So the word contract curve implies that if you start off from any point, let's say here, endowment point like this one, you're going to ultimately, when you trade, you're going to come at a point, your contract will end at a point along this yellow line. Because if the contract stipulates, let's say, why do you call it contract? I mean, these are two people exchanging goods, but you know, we economists are very very foolhardy that way that we think, okay, these people won't just exchange. They'll first write a contract about how to exchange and then they'll exchange. So what will be the terms of this contract? So let's say the contract stipulates that these people should come to this point. But if this point is not on the contract curve, then there is still scope for Pareto improvement. So these people can trade even further and make themselves better. So any contract which is drawn should actually put these people somewhere along this curve. But now the idea is, what is that one point which is going to be the equilibrium? Okay, so yes, it's fine. I mean, the contract stipulates you'll end some point along this entire line, but which point exactly is the equilibrium? That becomes the question. So to imagine this, consider a situation. So right now, these are just two people exchanging goods X and Y. There are no prices, anything. It's like bread and butter. You give me 1 spoon butter, I'll give you 2 slices of bread. It's working like this. Okay, so that's how the trade is happening. But suppose for some reason that this market has some fixed prices. The price of good X is, let's say, PX, and PY is price of good Y. Suppose endowment of agent A is XA comma YA. Endowment of agent B is, let's say, XB comma Y. So if agent A were to sell his entire endowment at these prices, what income will he draw? What will be the income of agent A if he just sells everything he has? Just look at these numbers and tell me what will be the income of this guy if he sells this endowment at these prices.
The XA PX plus YA PY.
Very good. PXXA plus PYY. So this is the income of agent A. Right. So agent A basically solves a utility maximization problem to maximize utility of agent A such that, suppose utility of agent A at this XA prime comma YA prime. I'm calling it XA prime YA prime because the final utility maximization can be different from XA YA. Okay, so maximize utility of agent A at XA prime comma YA prime such that Px into XA prime plus Py into YA prime is equals to income. Income is Px XA plus Py YA. So this is the budget constraint. This is the optimization. So how does this work? So you have some idea of utility maximization. So this was his original endowment upon which you draw the price vector. So this becomes the budget line. So this was his original point XA comma YA. This becomes the budget line. This entire thing becomes the budget line, which is Px into XA prime, which is basically this thing. This equation. So now all these points are along his budget line, and he just picks the point of utility maximization, which is going to be the point of savings. So he's going to pick a point of savings along these points. And the same thing happens with B, by the way. The same thing happens with B. Instead of A everywhere, you'll write B everywhere. The only thing that changes is the colors and A goes to B. So that's what will happen with B. So he's also selling everything off, and then he's going to the market and buy things. So if we look at the if we look at the budget constraint of A and budget constraint of B, let me write down budget constraint of both the agents. So budget constraint of A is Px into Xa prime plus Py into Ya prime must be equal to Px into Xa plus Py into Ya. Budget constraint of B is similarly Px into Xb prime plus Py into Yb prime must be equal to Px into Xb plus Py into Y. So basically what I can do is I can write this as negative. And then I can add them up. When I add them up, I'll get Px into Xa prime plus Xb prime minus Xa plus Xb plus Py into Ya prime plus Yb prime minus Ya plus Yb is equals to 0. Now Xa prime plus Xb prime is the final demand for good X. This is the total supply of good X. Because you remember, this is an exchange economy. The supply is whatever you are born with. Suppose you and your friend meet at India Gate. The total amount of bread is whatever the two of you bring together. The total amount of butter is whatever the two of you bring together. So the total supply is whatever you are born with for good X, that is Xa plus Ya. And total demand for good X is whatever you are demanding in the end, that is Xa prime X. So this final demand minus total supply is known as demand for good X. This demand minus supply, final demand minus total initial supply is known as Zx. Similarly, this thing becomes Zy. So the equation that I'm looking at is Px into Zx minus Py into Zy must be equal to 0, which implies that P dot Z must be equal to 0. Sorry, plus Py into Zy. Now Zx is also known as net demand of X. Net demand. That is demand minus supply, net demand. Now, when the Zx is positive, it implies that demand is greater than supply. When it is 0, it implies that demand is equal to supply. And when it is negative, it implies that demand is less than. Now come back to this identity P dot Z 0. This is a very important theorem which is known as the Walras law. P dot Z equals to 0. The price of any good, the price vector dot the excess demand. Actually, this is actually known as excess demand. Sorry, not net demand, excess demand. Excess demand. So P dot Z is 0, where P is basically a vector of prices, Px, Py. Z is the vector of excess demands, Zx, Zy. So the dot product of these two vectors will always be 0. And this is true. Remember, when deriving this equation, I did not use utility functions at all. I just used the two budget constraints, just these two equations. No use of utility functions. So the Walras law is actually true for all price vectors and all utility functions. whatever utility function you use, whatever price vector you take, the Walras law always has to be true. Okay. So let me write down this condition again: Px into Zx plus Py into Zy. Now Px and Py are prices, so they have to be strictly positive. Now, if Zx is positive, what will happen to Zy for this thing to be zero?
It'll have to be negative.
Negative, very good. It will have to. So basically, if there is excess demand for one commodity, if there's positive excess demand for X, there is negative excess demand for Y, which means there's excess supply for Y. So you imagine an economy which is only supplying two goods. If there is an excess demand for one of the commodities, it is imperative that there is some other commodity somewhere in this market which is facing an excess supply. I usually call a negative excess demand as excess supply. So if some commodity is facing excess demand, some other commodity must be facing an excess supply. So you see, when COVID happened, suddenly the demand for masks went up. So you see sudden increase in excess demand. So excess demand for masks becomes positive. The impact of that is that somewhere some commodity was facing a negative excess demand without even looking at what kind of market it is, what are the utility functions, what are the people. I'm not even looking at all that. I'm just saying that just because one commodity is showing excess demand, some other commodity must be showing an excess supply. It's a very powerful statement. Now the equilibrium is defined as the price vector such that Z vector becomes zero. You see, when when Zx becomes zero, Zy automatically becomes zero. So you reach equilibrium. So if there are only two commodities in this market, X and Y, you reach equilibrium in X, that is the market for X. If it clears, if demand is equal to supply for X, then demand must be equal to supply for Y as well. Okay, so it's as simple as that. Okay. So let's look at an example and see how to find excess demands, and we'll see how to yeah. So let's do this example. So utility of both agents are under root xy. You remember, you can always use xy instead of under root xy because it's just a monotonic transformation. The reason I keep giving root is because for you to understand that root say you can always go to xy without changing the final results. Monotonic transformations are okay in consumer. All right, so these are the endowments. Prices are fixed at 1, 1. You have to find the excess demand. So let me just write down everything. Utility is xy. Endowment of agent A. Endowment of agent A is 3, 4. Endowment of agent B is 5, 8. Px equals to Py equals to. If these are the prices, what will be the income of this guy? If he sells everything, what will be his income?
7
7. And this guy's income will be
13.
So a person with income 7 faced with this prices and utility equals to XA YA, what will be the utility maximizing bundle for this guy? Oh, you don't even need to work that much, man, because see, it's symmetric. Yeah. Income is 7, prices are 1 each, utility is also symmetric. So you're going to buy equal amounts of both goods, obviously. So if you're going to buy equal amounts of both goods, what is going to be the final point that you buy?
4,6.
No, you cannot even afford 4,6 because 4 plus 6 is 10. You have just 7 rupees. See, 7 rupees is, I'm saying, I'm giving
So
you the answer. It's
3.5, 3.5.
very good. 3.5, 3.5. All right. So this is for like really the first 2 chapters that we did. So you guys need to revise it. I mean, even without symmetry, you should have been able to do it. Similarly, what's going to be the point that this guy is going to consume?
6.5.
Very good. So this guy is going to consume 6.5, 6.5. So this is the final demand from A. This is the final demand from B. So now let's try to find what is going to be the excess demand. So excess demand for good X is total demand, that is 3.5 plus 6.5 minus the total supply. So total supply is 3 plus 5. So that is 10 minus 8. So that is plus 2. And excess demand for good Y is 3.5 plus 6.5 minus 4 plus 8. So that is 10 minus 12. So that is minus 2. So Zx is plus 2, Zy is minus 2. Prices I know are 1, 1. So let us analyze the Walras law. Px Zx plus Py Zy will be equal to 1 into plus 2 plus 1 into minus 2. So that is. So the Walras law holds. Okay, so the Walras law. So now the next obvious question is that if Walras law holds, then what is going to be the equilibrium? The equilibrium is the price vector. Okay, I've already defined it, right? Price vector such that Z bar is 0. So what I have to figure out is Px and Py such that this Z vector, Zx and Zy both become 0. All the Z, since we have only 2 goods here, X and Y, we are only considering Zx and Zy. If you have 10 goods, Z of all those 10 goods must become 0. That would be the equilibrium. So Px, Py such that Z vector becomes 0. So that's my equilibrium. Now the idea is that Px and Py, you cannot really take them as 2 different variables. The reason is that it's not the exact prices which matter, it is the relative prices which matter. So take for example a situation where price of bread is 40, price of butter is 50. Suppose you go to some other country and you find that the price of bread here is 80 and the price of butter here is 100. So the relative prices are not changing. So bread versus butter are equally costly. So suppose for simplicity, I assume the prices to be 80 and 160. So in this country, the market is basically exchanging one butter for two breads. The market rate of exchange is the ratio of prices. And in this market also the same rate of exchange is happening, because if you sell two packets of bread, you can buy one packet of butter and vice versa. So the absolute prices don't matter. What matters is the relative prices. So what happens is that we do not assume Px and Py as two variables. What we assume them as P, 1. We assume that Py is equals to 1 and Px is equals to some variable. Because in this market, there's actually no currency. There is no real currency. This is an exchange market. These prices are here to give us an idea of how to use our consumer theory in general. Because without prices, consumer theory does not work. But in reality, there is no currency. If there is no currency, what is the point of these prices? The prices are basically a mathematical construct we introduce to generate the concept of this relative trade which can happen. So the ratio of prices decides the ratio of trade which happens in the economy. And that is what I'm interested in. So this is going to be a very strong, very interesting or necessary assumption, because without this assumption, you cannot solve the general equilibrium. You have to assume one of the goods price as well. So if there are three goods, instead of assuming Px, Py, and Pz, what you assume is Px, Py, and 1. Any one good is called as the numeraire. The numeraire good. Numeraire good is the good for which price becomes equal to, or you normalize the price. You can call it either way. The point is, one of the prices has to be taken as 1, and all the other goods prices now become relative to this guy's price. See, this is how things started initially. Initially there was barter, but then came along coins, gold coins. So now everything was pegged against gold coins. So this thing is worth 1 gold coin. This thing is worth 2 gold coins. So price of everything was benchmark against this commodity called a gold coin. So gold coin became the common mode, and that's how it became the currency. Currencies are not natural. Currencies are an economic construct which basically help us trade. But that's how it came into being. Everything is pegged. So the price that you see, a mobile phone costs 40,000 rupees. So this is the relative price of a mobile phone and a 1 rupee coin. It's nothing but a relative price of a mobile phone and 1 rupee coin. So we call the 1 rupee coin as the numeraire in our economy. The price of 1 rupee coin is pegged as 1, and everything else is benchmarked against that 1 rupee coin. But since this economy does not have the 1 rupee coin, we can benchmark it with respect to any of the goods. So let's say good Y is the currency, and good Y's price is 1, and X's price is now just with respect to good Y. So P is the price of good X, 1 is the price of good Y. So that becomes the relative price. Fair enough. So now let's come back to the consumption set of good person X. This was his endowment point. Okay. Now, this is the budget. What is the slope of the budget? If prices are Px equals to P and Py equals to 1, what is the slope of the budget?
So P.
P, actually minus P. Actually minus P. So the slope of the budget line, the budget line is always Pxx plus Pyy equals to income. So the slope is always minus Px upon Py. So minus Px by Py is the slope, which in this case becomes minus. Right. So this is the slope of the. So now let's construct the Edgeworth box and see what happens. Suppose this is the IC of agent A and this is the budget line. Now both the agents are in the same economy. So the budget lines for both these people is going to be this common budget. The same budget line with a slope of minus P will be passing through the endowment point. So the budget line is basically a line with slope minus P which passes through the endowment. Okay, so in an exchange economy, budget line is the line through endowment point with slope equals to minus Px upon Py. The line through the endowment point with slope minus Px by Py is the budget. Because there's no fixed income. You see, if you change the relative prices, if you change Px and Py, the budget line changes in this manner. The slope changes, but it remains hinged at this point because whatever the prices are, you can always afford your endowment. Whatever the prices are, you can always afford your endowment. You can sell it and then buy it back. Right? You can always afford your endowment. So the budget line always passes through the endowment point and the slope will be equal to Px by Py. So this is the budget line, and suppose this is the agent B's difference. Figure 1. This is agent B's difference. Now what happens is both people try to find. So this guy, what he'll do is, this is the budget line, so he'll find the tangency on this budget line. So he finds the tangency point as this point. And agent B also solves his tangency. His tangency, let's say, happens at this point. So he wants this point. So the demand for agent A is this one. This is the demand for good X. This is the demand for good Y. And the demand for agent B is this much. This is the demand for good X by B, and this is the demand for good Y. So if you happen to, let's say, extend this demand here, you will see that the demand for good Y by agent A is actually this one. So this is XA amount, the demand for good X by A, and this is the YA. Not X, Y. This is YB, and this is Y. So YA plus YB is clearly greater than total endowment of good Y. So suppose this total endowment of good Y, which is this length, is this much. If you look at good X, and if I were to, let's say, extend this thing here, you'll see that the demand for good X from A is only this much. So this is your XA, this is your YA. So XA plus XB. Now XA plus XB is clearly less than total demand. So the total demand for good X is, sorry, the excess demand for good X. So this implies that ZX, which is the excess demand for good X, must be negative, and this implies that ZY must be positive. Total demand for Y is positive, total demand for good X is, sorry, excess demand for good Y is positive and excess demand for good X is negative. So coming back to my Walras's law, Px Zx plus Py Zy is equals to 0. Now this Zx is negative, this Zy is positive. Now general economic question, what happens to the price of a good when its demand is more than supply? For example, good Y here.
So
So
it
for good Y,
rises.
price rises. So if Zy is positive, it implies that my Py should increase and this should fall. Now this was my budget line. If Px reduces, now the slope of budget line is minus Px by Py. So the magnitude of slope is Px by Py. Now if Px reduces and Py increases, what should happen to the slope? Should it become steeper or should it become flatter?
So flatter.
Flatter, exactly. So that's the idea. So if you are in a situation where the markets are not clearing, where Px and Py are such that there is positive excess demand for some commodity and negative excess demand for some commodity, then the prices will arrange in such a way that the excess demands, they all become. So here what we'll see is in this economy, prices will adjust. You don't have to adjust them. The market will see, the sellers of good Y will see that there's huge demand for this good Y. Suppose good Y is price of masks, and suppose good Y is mask, good X is air tickets. So pandemic hits, suddenly people see masks are in demand, prices of masks will go up. People are not traveling, prices of air tickets will come down. So the market will adjust in such a way that prices change, and eventually you will reach a point where both consumers, so let me erase this thing. So ultimately what will happen is that a price vector will be reached such that the point which A demands at tangency will be the same as the point which B demands at tangency. And when that happens, when both of them demand the same point, at that situation, what will happen is that there will be no excess demand. So the condition for no excess demand in an Edgeworth box is that the demand point of both these people must be same. Both these people must be demanding the same point. So let's do a problem and try to understand how this thing will work. Okay, let's come back to the same problem and try to find the equilibrium in this situation. So obviously at 1,1, equilibrium is not reached because we see excess demands, non-zero excess demands for both. So forget 1,1. Let's start with everything same, 3,4 and 5,8, and try to find the prices at which the excess demands becomes zero. Okay, so endowment of agent A will be equal to 3,4. Okay, and endowment of agent B is 5,8. So now what I need is for these two agents to give me. Yeah. Now what I need is to assume some price vector p comma 1. So if I assume some prices p comma 1, remember utility is xy for both these people. Utility equals to xy. So MRS of agent A is equals to y a by xa, which should be equal to px by py, which is in this case p, which implies ya must be equal to p times of xa. Now budget constraint of this guy is p into xa plus ya must be equal to p into 3 plus 4. So if he sells this endowment at this price, his income is going to be 3p plus 4. And then ya is equals to xa. So what I get is 2ya is equals to 3p plus 4. This is coming from agent A. Now, similarly for agent B, if I solve this MRS equals to price ratio, I'll get YB is equals to P into XP. And the budget constraint is going to be equal to 2YB is equals to 5P plus. Okay. Now I'm going to add up both these equations. So twice of YA plus YB must be equal to 3P plus 4 plus 5P plus 8. Now YA plus YB is total amount of good Y, which is 4 and 8. So that should be equal to YA plus Y. So that is 12. So 24 must be equal to 8P plus 12, which implies P must be equal to 12 by 8, which is. So pretty simple, right? I mean, just use MRS equals to price ratio and try to work around with the equations. Start by assuming price is P comma 1. So this is going to be the equilibrium price vector 3 by 4 comma 1. So you can write it as 3 by 4 comma 1. Or you can multiply the entire thing by 4 and write it as 3 comma 4. Or you can write it as 30 comma 40 or 300 400. I don't care. As long as the relative price is 3:4. So the relative price Px by Py must be 3 by 4. That's all required. So in the exam, you can get an option. The equilibrium price vector is 3 comma 4, and then a bunch of other options. Then 3 comma 4 is correct. Okay, the relative price matters. It's not the absolute prices. So now the final thing is, what is the equilibrium allocation? So to get the equilibrium allocation, just put this P value here and here, you get YA, and then you put that YA value here and here, so you get X. Okay, so after that you can get XA, YA value. Okay, so that's how to find the equilibrium price vector.
So P is 3 by 2 then.
Oh yeah, it's 3 by 2. Sorry, 3 by 2. 3 by 2. So it could be 3 by 2 comma 1 or 3:2 or 300 comma 30 comma 20. Sorry. Yeah, but everything else remains. But yeah, you're correct. It's 3 by 2. So let's do a different example now. So let's say, okay, everything is similar. utilities and everything similar. Let me zoom out a little bit and show you this solution along with the next example. So in this example, endowment of agent A is 2,8. Endowment of agent B is 8,2. Utility is again X, Y for both of them. Okay, so find equilibrium price vector and equilibrium allocations. Find the equilibrium price vector and equilibrium allocations. You can use the proof that you're seeing on the screen. You can use it to understand how to go about it. Yes. Do we have any answer?
1,1.
One. Yeah, correct. Price vector is one. And did you get the final equilibrium allocation using it?
On it, sir. So 2,5 and 8,5.
2,5 and
8,5.
but that's wasteful. 2,5 and 8,4 total amount of good y is
8,5, sir.
okay 8,5. But if the price vector is 1, then 8 plus 5 is 13. This guy's initial income for the price vector is only 10. So if you're saying price vector is 1, he starts with an income of 10 and you're making him purchase something with 13 rupees. So that's not possible. So this is how you can check if your final answer is correct or not. And these things should hold up. Like his income, given any price vector, his initial income and his final expenditure must be the same. So once you find the income and the price vector, once you find the price vector, income is straightforward, and then it's just utility maximization. So it shouldn't take much time. The idea is very easy, right? So using the similar logic that we did earlier. So I know YA by XA must be equal to P, which implies YA must be equal to P times XA. And then I can use budget constraint. So 2P plus 8 must be equal to Pxa plus Ya, which must be equal to twice of Ya. Similarly, I'll get here 8P plus 2 must be equal to twice of Yp. And then I add these two equations up. So I get twice of Ya plus Yb must be equal to 2P plus 8 plus 8P plus 2. So twice of Ya plus Yb is 10. 8 plus 2 should be equal to 10. So must be 10 times P plus 1. Right? So 2P plus 8P is 10P. 2 plus 8 is 10. So this implies that P must be equal to 1. So once you get P equals to 1, after that, you just substitute this. So you get income of agent A is equals to this thing, 10. Px equals to Py equals to 1. So MRS, so then it's pretty straightforward. I mean, you have already found out these things. So YA must be equal to 2P plus 8 by 2. So that is equal to 5. And XA must be equal to YA by P from this equation. So that should be equal to 5. Now if YA is 5, YB must be equal to 5. If XA is 5, XB must be equal to 5. So they should all be 5, 5. So these are the final allocations. Okay. All right. So this was when consumers had well-behaving convex preferences. But they never ask you well-behaving convex preferences. They always ask you something different. So there are different kinds of situations, perfect substitutes. When both agents have perfect substitutes, when one has perfect substitutes, other guy has convex. Then you have perfect complements, both having perfect complements. One perfect complements, one perfect substitutes, one perfect complements, one convex. And then we have lexicographic, both having lexicographic perfect substitutes, lexicographic perfect complements, and lexicographic convex. So these are the other type of things. Most of the analytical stuff that we have done about contract curve, about excess demand, that would remain same. But obviously, we cannot use MRS as opposed to price ratio in any of these cases because they are not well-behaving convex preferences. So that's why they are very popular with exam. If you go back through time, through the past years, which I've also added here, there are a lot of past years, by the way. because it's one of the favorite topics for DSE and ISI also lately. They rarely ask questions from convex preferences. They always give you either perfect substitutes or perfect complements or something like that. So if you go or till 4-5 years back, perfect complements used to be lexicographic preferences used to be very popular. Now perfect complements have become popular. But we'll look at them. We'll see how to handle different situations. We'll look at all these cases. Hopefully, we should be able to complete it in the next class. And when we do, that would be the end of end of this section of microeconomics, and then we'll start macroeconomics. We'll come back to one more topic, that is public goods and externalities later on. So that will be another 2-hour topic along with trade. So trade and public good externalities I'll do after macroeconomics. So tomorrow's, next week is going to be the last lecture for microeconomics. All right. Okay. So let me. Hello. Yeah.
I just
So
said
let's.
okay.
Okay. All right. So let's end this class. I'll see you guys next week. Saturday we have discussion on meetings. See you guys next week. Bye.
Bye, sir. Thank you.
Thank you, sir.